Hi, part one of this topic was finished rather abruptly. Sorry for that. So we will start from there. So I was mentioning that Boolean equations can be used um, to write in different functions, and then in order to simplify the hardware, I mentioned different techniques in the videos. For example, I mentioned some of the axioms, some of the theorems. Then I mentioned how to represent a certain functionality, whether we want 1 or 0 in terms of truth tables. Then in the truth tables, when we um, create Boolean equations, we can represent output as sum of min terms. Min terms are using all the inputs, or product of max terms. Max terms use all the inputs. Then I also mentioned how k-maps can be used from truth table in order to simplify the Boolean equations. So smaller Boolean equations, fewer min and max terms on those means we will have fewer gates, mean we will have a simpler hardware architecture. Then after that, I went into building smaller blocks of combination circuits. Understanding those were important because it also gave you an idea of how combination circuits can be used um, to create a smaller functional thing, something very useful. How you connect different type of gates to create something with multiple inputs comes, and you can select one of the inputs which goes to the output. That is a multiplexer. Then we talk about encoders, decoders. Then we went on to arithmetic operations like adder, half adder, full adder. Then we look at a couple of different adder options, how they are implemented in hardware. We look into subtractor, how adder can be used as a subtractor, how we can use adders and comparators, how we can use adders, multipliers. In multiplier, we look at array multiplier or shift and add multiplier. Then we also look at a structure to implement divider using one full adder, a shift and subtracting. The shifting we use here, and I didn't look into that, but during the sequential thing, we will look into how we can shift within registers, shift left or right. So you can see that starting from simple gates, then interconnection of gates, Boolean equation with simplified Boolean equations using different methods, and then we create different building blocks. With these building blocks that we have, which are consist of different gates, and the gates are implemented most commonly on complementary metal oxide semiconductor, like where you can make a circuit with n mosses and p mosses. You have both type of transistor for each of these, each gate. Like you can make an inverter that can make an AND gate, a NAND gate, and NOR gate, exclusive OR, NOR, all those type of gates. Then using those gates, you can make an adder. You remember adder? We had for a sum and carry, we had different gates for full adder, half adder. So when we talk about adder, it's like the next level of abstraction. Okay, full adder. I would never talk about how many gates it has, right? So I would always talk about adder. Whenever I talk about adder, I really mean those type of different gates used inside. And so similarly, when I talk about the gates, I don't talk about the transistors, the PMOS and NMOS notations. I don't talk about those transistors inside. So I just talk about the overall NMOSs, PMOSs. So these are different abstraction levels to make our life easier, to make the bigger circuits, so that at each level we are talking about certain hierarchy. It doesn't mean that when I talk about adder there are no gates. Definitely means there are gates. It definitely means there are transistors. So actually, if you look and open up adder in a layout and on a chip, it will have only transistors. But we have defined gates and these adders, and the next level up I'll talk in a minute, to create different abstraction level in order for us to design things, to verify things, and also to generally refer to those easily. Now, how these are implemented? So, using set of these, a good computer system, digital system example or digital circuit example is a CPU, which I will, in the next topic, I will start videos on giving you a little background of a CPU, and we will get into ALU. But if you think of a good digital system is a CPU design. CPU design, you combine different components from here. And you also have sequentials, which we haven't studied, registers, latches, memories, type of things. So within CPU, okay, you define the functionality of CPU, or you create the CPU in hardware using what? Using HDL, hardware description languages, such as Verilog, VHDL. So you describe everything using this one. And that is called, that abstraction level called is microarchitecture. It's like you define things in terms of building blocks. And you code that, or you implement that in hardware description languages. You simulate that design using simulators to verify that it's really doing the functionality that you design it for. But once you have defined an HDL and you want to convert that into transistors, you can convert it into intermediate format. So the basic building blocks, like are these different things, and some of them can be even some of the logical gates like AND or exclusive. Like, for example, you want to do this or this, or you want this and this. Those type of functionality can be described with different logic gates. So arithmetic, logical gates are used under the hood. Okay, these certain gates that we know will be repeated, we design them individually, separately, and optimize them. Those are called standard cells. I touched on these one earlier on, and these will be important later on. Standard cells. I had a video on standard cell as well, especially from the combinational circuits. Standard cells. These will be simple gates, logical. These can be muxes. These can be adders. These can even be very dedicated multipliers or dividers if that is the you want to really optimize. Sequentials are registers and latches, we will talk next. So you really optimize certain key. For example, I can take an adder, simple full adder, which is you have A coming, you have B coming, you have Cn coming, it will have a single output S, it will have carry. I will really optimize it at the transistor level. So I will create different gates which are made of different transistors. I will really interconnect them, optimize them such that I create a very compact, very high performance, very low power type of design, and then I will use that as my standard cell. And then when I take this RTL, I will use synthesis tools. Synthesis tools are going to convert this microarchitecture into standard cells. And standard cells are already, I have a layout version of those using transistor which are optimized. So you see the methodology that we are using from RTL down to using synthesis down to standard cells, and then we create the what we get is a net list of standard cell. And then net list is what we create a layout of. We verify timing, design rule checks, and layout, and all those type of things which we'll cover under physical design. Hopefully this gives you an overview of the bigger picture that we have. Okay, I think this is it for now. In the next video, I will talk about, I want to, before we finish combinational circuits, I really combine the functionality that we have studied together in the form of an ALU, which is inside the CPU that I mentioned in microarchitecture. So in the next video, I'll give a little bit overview of the computer architecture and go to the ALU, and we will design ALU. And after that, we will head to sequential design, latches, registers, and all that, and look at the functionality of those elements and the logic design. All right, that's it for now. Thank you so much for watching. See you next time.